Okay, so in this video we're talking about beta stability. So to start off, here is a standard common emitter amplifier with resistor biasing. So if we run this, look at the output, you can see, look at the peak to peak. We have 2.8 volts peak to peak. We have an input of 10 millivolts. So we have a pretty high gain amplifier. So let's go and look at the data sheet for 2N3904, which is right here. And we're looking for beta, which is our current gain. So in this one, they call the DC current gain HFE. So this is our beta. We typically have about a milliamp. So it's like right in here. So it's somewhere between 70 and 300. So you can kind of see that the beta changes between 100 and 300. So let's go back and see what happens if we change our beta to, so here it's 2.83. So what we're going to do is we're going to use two different betas. So we're going to use a dot step. Dot step we're going to do for our NPN. We're using a 2N3904 transistor. We want to vary BF, which is our forward beta, and we want to go 100 to 300 with a 200 step. So that's just going to give us the 2, 100, and 300. So we run this, and you see that we get 2. So you can kind of see this one is a lot bigger than that one. So if we check our gain again, so this is doing the red one, and if we put our cursor over here and if we put our cursor right on here and right click, you can see that that is the 100, and it has a peak-to-peak amplitude of 1.15. Now, if I click on one of these and I use my arrow, I can switch which one it's on. And so this is the 2.83. So you can see 2.83 versus the other one, versus the 1.15, we have almost a 3 times difference in the gain because of the change in beta. So let's go and look at what is the cause of all of this. So our basic circuit, if we do our Thevenin equivalent, and this was 10 volts. Okay, so our gain is equal to GMRC minus, which is equal to minus IC over VT times RC. So you see so what all we have to worry about is this change in IC. Well, if I look at this loop, so I do the KVL loop around there, and we see that IB is equal to V Thevenin minus 0.7 over our R Thevenin, which is R1 in parallel with R2. And if I want to plug in the detail, remember that this is 10 times R2 over R1 plus R2. Okay, so you see that my IB is constant, but my IC is equal to beta IB. So if my beta changes by a factor of 3, my IC changes by a factor of 3, and then, or decreases by a factor of 3, then this goes down. So what we see here is that as my beta beta fluctuates by the day or the temperature or the BJT, then I'm going to get a different gain each time. So what we want to do is we want to create something that is beta stable. So I want IC to be independent of beta. So in order to make IC independent of beta, I need my IB to decrease as my beta changes. So in this loop right here, I need to get a beta dependence. I'm going to do that by putting a resistor down in my emitter. So this is what my circuit is going to look like. And we call this R1, R2, RC, and RE. Okay, so what we're going to do is we're going to go in here and do our Thevenin equivalent right there again. So then this looks like this. Okay, that looks like that. And so now, again, when I do my loop around here, I get minus V Thevenin plus R1 in parallel with R2 times IB plus 0.7 plus RE times IE equals 0. And so I want to convert my IE into an IB. So I have minus V Thevenin plus 0.7 plus R1 in parallel with R2 times IB plus RE times beta plus 1 times IB. And that converts my IE into an IB. So if I look right here, now you see that my IB is going to be equal to V Thevenin minus 0.7 divided by R1 in parallel with R2 plus RE times beta plus 1. So now when we're calculating our IC, which is equal to beta IB, that's going to be equal to beta times V Thevenin minus 0.7 over R1 in parallel with R2 plus RE times beta plus 1. So what we see is that here is a beta and here is a beta. So if I can make it such that this part is negligible, then I get an IC is equal to beta over beta plus 1 times V Thevenin minus 0.7 over RE. And if my beta is large, then this part here is effectively equal to 1, and then we see that my IC is completely independent of beta. So my IB is changing with beta, but my IC is not. And since my gain equation depends on IC and not IB, it is going to become beta stabilized or independent. So in order for this to work, I use the approximation that RE times beta plus 1 had to be my dominant term, so that has to be much, much greater than R1 over R2. So if I do this approximation, then that leads into beta stability.